Hey everyone, welcome to this video. Today I'll be presenting DualMap, online open vocabulary semantic mapping for natural language navigation in dynamically changing scenes. This was authored by the researchers at Zhejiang University and published in the IEEE Robotics and Automation Letters Journal in 2025. This paper tries to address the following fundamental problems with the existing mapping systems. Most semantic mapping systems assume a static environment, and when objects are relocated, the system does not immediately remove them, but it updates its belief and gradually decays it. But this can be an issue as it causes the map to accumulate ghost objects that exist even though they were removed from the environment. And this can mislead planning, navigation, where like a robot may move toward a mug that is no longer there, or try to avoid obstacles that don't exist. Basically, it forces a lag between the map and the reality. The paper also addresses the high computational costs involved in feature matching because close set detection may not generalize as well in open world environments where objects may go undetected. So there's this requirement for a low latency open vocabulary map, which also enables natural language based querying. This paper compares its results with Chronos, which excels at handling dynamic objects but uses closed set detection. On the other hand, there is concept graphs and HOVSG, which are both open vocabulary but struggle with dynamically changing objects. So DualMap is open vocab and robust to dynamically changing objects while being light enough to be able to do all of this in real time. Okay, let's take a look at how they do it. So instead of maintaining a massive, expensive map of everything, the system splits the world into these two representation. One is the local concrete map, which is basically a detailed 3D semantic point cloud that is only built and maintained locally around the robot. And there is the global abstract map, which is a lightweight topological graph of what the authors call anchor objects. There is a table or a counter, and volatile objects. There is a book or a mug, etc. So the robot uses the global map for high-level planning and the local map for precise localization of objects. So this combined together would eliminate the computational burden of maintaining a dense global map. Okay, high level picture of the pipeline defined in the paper. So the front end uses a YOLO V8 detector for common objects and SAM for objects for which are not in the closed set. The non-overlapping objects are fused and augmented with text features using mobile clip, and these detections are used to build the local map, and the global map is also built simultaneously where the system abstracts the data and links objects to their nearest anchor point. For example, this might include like linking a cup to a table or something. Now, when we ask find the cup, the system retrieves the likely anchor, for example, the table, and plans a path there. And then it uses the local map to verify if the cup is actually there or if it has been moved. If it is moved, it just updates the map and checks the next likely anchor, probably the kitchen counter, for example. And then the pipeline repeats from there. Ah, finally, the results section. No surprises here. So the authors compare DualMap with concept graphs and HarvestG for the replica dataset. I have plotted the graphs in the log frame over here, so don't let the directions trip you up. The mean IOU is similar among the three, but DualMap still outperforms the rest. And we see a huge difference in the ODR, that is the object density ratio, where concept graphs and HarvestG score 2.02 and 3.81 respectively. DualMap scores almost a perfect score of 0.97. The time per frame metric is where DualMap implementation really outscores the competition. Concept graphs and HarvestG use 4.18 seconds and 4 seconds respectively, while DualMap uses barely a fraction of that at 270 milliseconds, which is outstanding. The authors also validated the results on real world dynamic scenarios like, for example, in anchor updates. where an object moves slightly but stays with the same anchor. In this example, the cup moves but it stays on the table. And also, they were also validated on the cross anchor updates, where the example says a mug is moved from the table to a shelf, and DualMap was able to handle both of these situations significantly better than the static baselines. All right, let us see it in action. This is a visualization using the rerun viewer, and this processes the author's original Rosbach data. It was known as HN3D. And here we can observe the local concrete map, which is being built in real time on the left over here. And you can also see the point cloud, which is dense and colorful, and you see multiple objects are being segmented and being placed in the 3D map. And on the bottom right over here, we can see the annotated images as well. Okay, here are some of the limitations that are pretty much made clear in the paper. First, it's a mapping system and requires the robot to already have a robust external localization pipeline which is running parallelly. So if the robot drifts, the map breaks. Secondly, the it relies on pre-generated scene context. What I mean by that is it doesn't query an LLM during operation. It just preloads a list of likely objects based on the scene at startup, and it is able to handle relocation but not tracking. So if you walk in front of the robot, it treats you as a noise, not as an actor. And finally, and I think this is one of the most interesting ones, it doesn't yet understand human object interactions. It is purely geometric and semantic understanding, but not a behavioral one. So to conclude, DualMap bridges the gap between semantic understanding and dynamic robustness. The strategy is to plan globally and verify locally. It enables robots to operate in real world with long-term autonomy. Thanks for watching the video, and I hope you consider subscribing to my channel for related content. Thank you.